was the other thing I wanted to talk about in experiment A was the density of water. What should the density of water be, roughly? 1 gram per milliliter. If you're getting like 480 grams per milliliter, is something right or something wrong? Something's wrong. You're using the table wrong, or 100 or 50 or 30 grams. It should be around 1, a little less than 1. And so, did you guys figure out how to use that table in the book? No. Okay. Yeah. So if your density is coming out the weird density, then you're using the table incorrectly. So take a look at it again, because on the vertical column is the Celsius degrees. On the horizontal column at the top is the tenth of a degree. So it'd go 24.0, 0.1, 0.2, 0.3. But the density, does the density of water change that much? It's around 1. It doesn't change much. And so in order to see a change in the density, you have to go typically beyond like 2 sig figs to 3 sig figs or 4 sig figs or 5 sig figs. And often the first 3 digits of the density doesn't change for a pretty wide range of temperatures. And so rather than writing the first 3 digits over and over again, they just leave those off. They'll just, when it does change, they'll write it. But when the first 3 digits don't change, they'll omit it. And so keep that in mind. And also the formatting of the table, the columns, sometimes they have to put a little asterisk there, meaning you got to go back to the previous first 3 digits, or you got to go forward to the next first 3 digits, that kind of stuff. So see if you could figure that out. It's around 0.99 something, right? All right, any questions on this report sheet? No? Oh, you'll turn this in at the end of the lab, okay? Usually I don't. Usually I collect these at the beginning of the lab, but I was supposed to talk about this last lab period, but I forgot to. Today's, there's a lot of dead time today as we're filtering, and so filtering does take time. And so what have we done so far in experiment 1B? We've somebody describe it to me. What we've done so far. We've gotten an unknown, right? Solid. And then you did what to that? Added what? What was the purpose of adding the water? You added water to do what? Uh-huh. Yeah. Basically, it's not adding water. The first step of this is to dissolve it. Why do we got to use whatever means possible to dissolve it? Why? Whatever means, it might not have been water. It might have been a whole bunch of stuff we might have to use to get it to dissolve. When you typically have an unknown, nobody's going to say that unknown is going to dissolve in water. It might not. Why do we need it to dissolve? Like Scott was asking about this report. The experiment A report's kind of mindless, because all you do is you do a couple of calculations, you fill out the blanks, right? It's pretty easy. But in a typical report, it's not so mindless. In a typical report, you have to describe things to the reader. And so we're only going to do one typical scientific report this semester. All the other reports are going to be pretty basic, not your standard report. In a typical report, once you collect all the data, you just don't do the calculation. You do the calculations. And you think about what you did in the experiment overall. And so. So what did we want to dissolve it for? Name? Name? Giovanni? Okay, what did we want to dissolve it for? To break it up into ions, but the purpose of breaking it up into ions is to do what? Is to... Well, why didn't we just leave it in the solid phase? You know, this is all stuff I was talking about on... what day did we start this? Thursday? You know, so I'm just reviewing. Make sure you got it. Did you get? We break it up into ions too. We need to do what?
You're trying to free the sulfate.
Free up the sulfate, right? Because the sulfate is locked in the solid phase, right? And so, you know, I was talking about this report. This is a typical scientific report, and so you're going to have to think a little. Actually, you're going to have to think about this lab. This is not a lab where you can just blow off everything and then just do the calculation and turn in the report. This is a lab that you're going to have to do a formal write-up. In that formal write-up, you're going to be explaining the exact same stuff. You know, basically, it's very easy. You just say what I've been saying about this, and that's your description. And so, but it's very difficult, too, because, you know, a lot of people don't pay attention because they don't think it's important, and then later on they come to me and they ask me what was going on in the lab. But it's very simple. You dissolve it so we can free up the sulfate. We free up the sulfate so that we can isolate the sulfate. How did we isolate the sulfate? We put barium chloride, and then we generated a precipitate. And so hopefully your precipitate is nicely coagulated today. And so we're going to have barium sulfate solid here. But there's a whole bunch of other stuff here. You know, this. And so we haven't completely isolated it yet. We need to separate out the... You know, we're isolating the sulfate as barium sulfate because now we know what it is. We know what this solid is. The solid should be... Hopefully the solid should be pure barium sulfate. But right now it's not really pure because this is what we call a heterogeneous mixture. It's got a mixture, a whole bunch of stuff, right? And so we really have to isolate this. In other words, we have to separate it. And so the easiest way to separate it out of precipitate from everything else is to do a filtration. And this is what we have for the filtration. For the filtration, we have these filter flasks. The filter flasks, you know, are unstable. You know, these don't really stand up very well, especially when the hoses are attached to them. And so we can use the utility clamp here to help us, or a ring on a ring stand. Yes. All right, this is a filter flask with an attachment here. This attachment, we have a Celis crucible. We can insert that in here. The Celis crucible is just a really fancy filter. These are expensive, so be careful with this. Here. Okay, this isn't so secure. You'll probably want to lower it down so this doesn't pop off here. Okay, then we have to hook this up to our vacuum. Our vacuum, we used to use these water aspirator vacuums. You know, water flow would create a vacuum there, but that's such a waste of water. We have a vacuum pump here. With our vacuum pump, if we hook the hose up directly to our vacuum pump, we run the risk, you know, if this thing overflows, then liquid would get sucked into our vacuum pump. If liquid gets sucked into our vacuum pump, it'll destroy the pump. And so liquids are not compressible. And so what we have is we have a trap. So if this one overflows, then water will get trapped here before getting pulled into. Now, if this one overflows, then we'll destroy the pump. We don't. It's a very expensive pump, so we don't want to do that. This is vacuum tubing. It's heavy walled. Have you guys done vacuum filtrations? No? All right. So what we'll do is we put the heavy wall tubing on our trap here and then connect this to our vacuum here. Okay, this is a pressure relief valve here. In other words, this is just a screw clamp on some rubber tubing. Yeah. Now I got vacuum here. Then I attach it to this arm here. So this should be alright, so I'll have to clamp this down too. Just temporarily counterbalance that. All right, so we should have decent vacuum here, so you'll want to check it, you know. Actually, this is pretty decent vacuum. You have the pressure relief valve to break the vacuum if you need to remove any components. But here we can check this, so we'll close this. That's pretty good. Okay, then you want to test. You know, you want to test this for clogs. So you just flow some water. Do you see the drip rate there? That's pretty fast. Without vacuum, then the drip rate slows to basically nothing. Actually, here, let me get rid of this vacuum completely. So I just filled up the crucible with water, but you can't see any drips coming through. And so this is really going to speed up the vacuum. So if you have some unclogged crucibles here, today should be fast. If your crucibles are clogged, then it's going to take the entire lab period. You know? And so that being the case, how do you want to filter? What we want to do is we want to trap the precipitate and remove everything else. And so how do you want to filter? Do you want to stir it up so you get a cloudy suspension and then filter it? No. What you want to do is you want to filter out this stuff first, the liquid phase. The liquid phase is called the filtrate, supernatant, precipitate. What is the liquid phase called? Filtrate. Supernatant? Yes. Precipitate? No. And so what we're going to do is we're going to pour this off. When you pour this off, usually what people do is they use a stir rod. Like this. And then just pour it so that the flow of the liquid goes down the stir rod. Let's see how this works here. Oops. You don't want to splash it on the outside, so you want to be careful with this. And so, actually, that's not working so well. So if you have a beaker with a little lip here, then that works fine. Just use the lip rather than the stir rod because less chances splash. And so you just gently pour off all the liquid phase, and then you don't filter all. You just need to leave a little bit in there. With a little bit of liquid left, then stir it up, get a cloudy suspension, and then filter off the suspension. Okay. And so we should have a precipitate caked on the bottom of our crucible. But is this precipitate pure barium sulfate? Now we just filtered it. Is it pure? No, because these crystals are wet, and they're wet with the supernatant slash filtrate liquid. Is the supernatant filtrate pure water? No, the supernatant filtrate, this stuff has a lot of other stuff inside there. The other stuff would be barium chloride excess, the cations that were originally in there, and any other anions that were originally in our unknown sample. And so there are salts, dissolved salts on here. And so the barium sulfate is wet with filtrate. And the filtrate is not pure because if we just went ahead and took off our barium sulfate and then dried it in the oven, do you know what's going to happen? All the water is going to evaporate, leaving all the salts, barium chloride and any other salts that are present in that filtrate. And so we don't want any salt deposits forming on our barium sulfate. And so do you know what we do with precipitates after we filter them? We have to wash them. And so how do you wash? Okay, you just wash it with water, right? Just wash it with water. Just pure DI water. Rinse off all that salt water off that. Okay, but there's problems with washing. Can somebody tell me some of the problems with washing? Washing is not so easy. You just don't get DI water. DI water would give you a nice spot-free rinse. You know, they use DI water at car washes and stuff. Spot-free rinse. So we want our crystals spot-free. We want to give them a spot-free rinse, right? But if we use DI water, what could potentially happen? We don't wash with DI water. We're going to wash it with a dilute acid solution, hydrochloric acid solution. And so we put some, we never know what's in these water bottles. If you don't know, dump it, rinse it, and fill it with DI. But one of the things we're going to put in today is hydrochloric acid. Just make a really dilute solution of hydrochloric acid, and that's what we're going to use to wash it. Because if we wash this with DI water, what could potentially happen? Oh, this would be like a pre-lab quiz. Explain what peptization is and how we can avoid peptization. That would be a typical pre-lab question. And so how many of you know what peptization is? How many of you read the experiment? Yeah, no? It's in there. Peptization. What is peptization? You know, pre-labs are closed book. You'd have to do this from memory. If you don't, let's say, this is right, the reason, at the beginning of lab I always, check if there are any questions. Those are questions from the reading, any confusing things in the discussion or confusing things in the procedure, I want to get cleared up. And so one of the words, new words, would be peptization. I think filtrate, supernatant, you've dealt with those. Precipitate, you've dealt with that. You have it, Sam? Okay. Right. The risk is if you use DI water, you're going to peptize this rather than coagulate. In other words, it's the reverse process. You spend all that time doing what to coagulate it? What was that process called? Not condensing. There's a fancy word for it. What was that word for coagulating the colloidal precipitate? Starts with a D. Digest. You spend all that time digesting these. You don't want to ruin it. And so we use dilute HCl to rinse this off. But the problem is can you tell, if you had a, by looking, can you tell the difference between, by looking at these two, can you tell which one is DI water and which one is tap water? Tap water has minerals dissolved in it. Which one will leave spots? Which one will give you spot free? By looking at it? They look the same, don't they? You can't tell the difference. Sometimes the minerals have smell, sulfur or something like that, but they look the same to me. And so how do we know when we've washed off all the filtrate? How do you know how much is enough? Well, the easiest thing is just overdo it. If you overdo it, for sure we're going to wash it. And so just keep spraying, spraying, and spraying, and spraying until you're absolutely certain you've washed every surface of every crystal in there, right? And then some. But there's a problem with washing too much. Do you know what the problem with washing too much is? We don't want to wash too little, otherwise we might leave salt deposits on our crystal. We don't want to wash too much, because if we wash too much, we have the risk of not peptization, something else. We're using HCl. Why does HCl prevent peptization? That would be a question, but that's something you just read. You could read. I'm not going to. What is the risk of washing too much? The risk of washing too much is that barium sulfate is not 100% insoluble. A little bit of barium sulfate will dissolve. And the more and more you wash, obviously the more barium sulfate you're going to lose. Right? And we don't want to lose any sulfate that we captured. We need to make sure we have all the sulfate that was in our original unknown precipitated. Okay. And so how do I know when my wash is done? This is like, okay, let's say you have a muddy t-shirt. You're in the backyard with a hose and you're going to wash off the mud, but you're going to do it blindfolded, right? And so you're spraying this muddy t-shirt blindfolded, and then you got to figure out when all the mud is off the shirt. And so spray, spray. How long do you spray for? Because we're essentially blindfolded here. We can't see it. We can't see when all the mud is rinsed off all the crystals, can we? And we don't want to spray too much. There's, water shortage or whatever else, or other reasons, losing the barium sulfate. The shirt's not going to dissolve. How do we know when we've washed enough? We're adding what to this? We're going to add sulfate, but why would we add sulfate? I mean, that's crazy, because if we add sulfate, isn't that going to screw things up? Because all we've been doing is trying to figure out how much sulfate is in our unknown, and if we're adding a whole bunch of sulfate, that'll really screw things up, and it would. And that's why some people really screw things up, because they add sulfate to the wrong thing. They just miss the boat. They put sulfate in here. You put sulfate in here, you know what's going to happen? If there's any barium around, it's going to make more barium sulfate precipitate. Right? You don't put sulfate in here. Do you know where you put sulfate? Not here. You put sulfate here. Why are we putting sulfate inside the rinse water here? Yes, That's exactly. Obviously, you know what's going to happen? The first wash here is going to contain barium ion because there's a lot of excess barium that we added. And so if we add sulfate to the first washing here, then forget it. It's going to precipitate. And so what we do is we break down the apparatus here carefully. Oh, the vacuum is still on. We break down the apparatus carefully, trying not to spill that. And then we dump this. And then, actually, we don't dump it there. We're going to dump it into waste over there because it has barium ion. Barium, remember, can be toxic. And then we're going to rinse this. Why are we rinsing it? To make sure there's no barium. And so I would say, you know, the first washing for sure is going to have barium in it. The second washing, maybe not. So I'd probably test the third washing or something like that, you know, or the second washing, whichever. Okay, so now this is clean, the flask, you know, reasonably clean. Doesn't have to be perfectly clean. And then give it another wash. Your final wash should be free of any barium ions, because we know for sure that in the other stuff, we know for sure there's going to be excess barium ions in here. And so we wash this. Now, if we test this washing, with some sulfate in here, and we see a precipitate, then that tells us what? You got to wash it again. So dump, clean, and wash again, right? If we add sulfate to our washing here and we don't see a precipitate, then that tells us it's clean. So stop washing. At least we know we've washed all the excess barium off there. And if that's the case, then most of the other stuff should be gone, or all the other stuff should be gone as well. All right, but the problem is now this. We wash with HCl, and now we have, we don't have pure barium sulfate. You know what we have here? We have barium sulfate solid that is wet with HCl. And so now this is the problem. How are we going to wash the HCl off? Now should we use DI water to wash the HCl off? Yes or no? How are we going to get the HCl off there? We aren't going to use DI water because of what? So let me talk about the report a little bit. In the report, the most important section is called the discussion section. In the discussion section, you're just describing the experiment, you know, all the chemistry that's happening in the experiment. For example, in the discussion section, you wouldn't say add water. You know, I take the unknown, add water, then I add HCl. You know, you're describing what's happening. Why are you adding the water? You know, why are you adding the HCl? What's the purpose for that? You know, the obvious questions are going to come up. Why are you washing with HCl? You know, you can just outright state we're going to wash this with HCl, but you have to describe the chemistry that's happening in the report. You know. And so for this particular experiment, like I said, this is a little different because I'm going to talk about it more step by step than the other experiments. The other experiments, I'm just going to let you go at it, figure it out yourself. This one, I'm going to spend more time talking about it. So this is why I'm repeating myself. But anyway, for the earlier stuff, this is what with HCl. Are we going to wash the HCl off? No, we don't have to wash the HCl off. You know why? We're just going to heat it. If we heat these crystals, what's going to happen to the HCl? HCl is normally a gas. Drive the HCl off. Not only will we drive the HCl off, we'll also drive the water off. And so what we're going to get is we're going to get dry barium sulfate here. Hopefully this is pure, assuming everything went okay. Hopefully it's pure. Dry or anhydrous barium sulfate is what we should form in this particular experiment. But, okay, then next time what we're going to do is we're going to cool these and weigh them. And so what you need to do is, you know, it's too hard to scrape the precipitate out of here to weigh the precipitate. You just leave the precipitate in here. And so what we need to do is we need to weigh these crucibles. We need to weigh the crucibles. But, you know, the crucibles, they might look dry, but are they really dry? No. Because of surface absorption of water. And so the same procedure. With the crucibles, they've been dried in the oven and then stored in a desiccator to cool down. When you pick up these crucibles, you don't have to cool them, you don't have to store them in a desiccator. You're just going to pick them up and then go weigh them. When you weigh these, should you handle them with your fingers? No. Handle them with a paper towel or something. And they're numbered for you. So you should have 1, 2, 3 at the bottom. And so we know the mass empty. We cool and weigh this. We're going to heat this, you know, overnight, over a couple of nights, and then cool and weigh. When you cool and weigh, you're going to have to do this in a desiccator. And then quickly weigh these on the balance. After we have the mass, then we're pretty much done. You can return the crucibles. This is going to be for next time. Along with any excess unknown, the numbered beaker, and the ribbed watch glass back to the stockroom. You don't have to clean the crucibles. You know, there's a special procedure for cleaning these. And so now we have our barium sulfate. Is this pure? Yes? As pure as you want it to be? I want it pure. I want it to be 100.00000% pure. Is this pure? We'll have to think about this. What makes you think it's pure? Because somebody is going to argue that doing all this, why do you think it's pure? Why do you think it's barium sulfate? Somebody's going to want proof. What kind of proof can you offer them? This is why these reports aren't so easy. These reports aren't so easy because you don't take things for granted. Somebody's going to confront you about this and say, okay, prove it to me that it's pure. This is why you're writing the report. The whole discussion section of the report is to lead to this conclusion that we're isolating pure barium sulfate. How strong? Is your argument that it is pure barium sulfate? Depends on what you write in there. Okay. Well, anyway, that's it for the discussion.
Can you just explain the report a little bit more? Because I don't recall that you went over it too in depth.
I haven't gone over the report at all.
Okay.
I'm not. The most important thing about the report is to understand what's happening in the lab, because once you clearly understand what's happening in the lab, then writing the report is very simple. You know, it's just describing what's going on in the lab. And so the actual report we're going to spend the entire semester covering. Basically, we're only going to do one report. In the past, I've done 3. I used to have Chem 1A students do 3 reports because I figured, well, if UCLA is doing like 10 formal reports, you know, 3's reasonable. But then I